Your pity, please. Mr. Houghton just spent half an hour recording this lecture, and then he just felt like it wasn't up to snuff. I got confused by a diagram, and so we're going to try it again, because nothing is too good for my students. Maybe it'll be a 20-minute lecture this time, because I'll know what I'm doing. I want to return to this wire carrying a current in a magnetic field that is going away from us, and I would like you to apply your knowledge of Hall, the Hall effect, to it, and tell me which side of this wire would have a higher potential. Now we are going on, so you put that on your worksheet. We are going on to only take a length L of wire. So that's going to be important to where we're trying to go here. That I want to write down the formula, which is the definition of magnetic field strength. So you stop the show, put down that formula. It says F equals, and see if you can pull it out of your head. It's good practice. So here it is. I hope you stopped the show. Next, I would like to consider this V here is the velocity with which these charges are moving here in this wire. And of course the charges that are moving are actually electrons that are going up, and this velocity would be what we would call the drift velocity. Given that you are moving at this velocity, how long would it take for a charge to move that distance L? What is the time to go L moving at that velocity V? And you write down that formula. T equals. Then you start the show again, and that was not much of a challenge, was it? Now what I want to do is take the fact that the current flowing in this wire is related to the the current, the charge that passes a point, the charge that is going to pass the end of the wire in this time t is going to be equal to the current times the time. That's the definition of current, that we choose a point on the wire and we look at how much charge passes per unit of time. So there you have that, but then for t I will put in that quantity. Now I'm going to take this and put it back up here for Q, and I end up with this formula, which is a good formula. It will work nicely for you. You can derive it from that if you ever need to, but it's probably better to just memorize it. It is rather equivalent to that formula there. You could speak of it perhaps as the definition of magnetic field strength. This time it is current times L instead of charge times velocity. And that L is a vector quantity which is being crossed with B, much as V was being crossed with B. But we have the trouble. What direction is L? And the direction of L is going to be given by the direction of the current. That vectorless quantity is once again going to determine the direction of L. I is a scalar, but L is a vector whose direction comes from I, and so you have that result. And now you will apply that result as you do checkpoint 4. Next, we're going to start talking about the magnetic dipole, which was the purpose of the title of this unit. That this loop of wire, loop of current, is what we would call a magnetic dipole, and we will get much more into the details of that in just a minute. Let's look at this loop though, with current flowing around as indicated by these black arrows. That current carrying wire is placed inside of this green magnetic field, which is produced by these permanent magnets. Doesn't have to be. I don't care how the magnetic field is produced, but I have a current carrier inside of a magnetic field. The current carrier, of course, is making a magnetic field, but that's going to be an intrinsic magnetic field. That magnetic field would interact with this extrinsic magnetic field to give you force. Alright, so current flowing this way, magnetic field going that way. Can you agree that they got the force correct here? What they call force 3 for this length of wire, whose length is A. Over here, the current is flowing the opposite direction. The magnetic field is still the same, so we are not surprised to see a force in the opposite direction, force 1. There is also a force 2 along this wire whose dimension is B. Will you please, on your worksheet, tell me what direction that force would be? And back here, there will also be a force, and it would go in the opposite direction because the current would be flowing the opposite direction here and here. So those two would cancel one another out. But these two do not cancel one another out because they are not collinear like these two forces were. That here you have a couple, and that's going to give rise to a torque. And let's look at that torque. That it's going to be, here is the pivot, so we would go an arm of 1/2 B, and then we'll cross that with the force that is acting at that arm from the pivot. But that force is going to be equal to IL cross B, that result we just got. And so this is an expression for the torque. Let's get a picture here that we can look at. That we are of course missing force 2 and force 4, but we don't care. Here this arm, 1/2 B, and then the force. And so you have this cross product. Now that cross product means that you are going to be doing here, this current, that black dot there, that current is going to be perpendicular. It's in a wire coming straight towards us. So it's perpendicular to the magnetic field and will always be perpendicular. So this cross product gets us a sine 90. ILB sine 90 comes out of that cross product, and sine 90 is of course 1. But this cross product here is a little more problematic, and I'm going to have to write a sine theta, which is going to be that theta there. But what is this? This is the direction of B crossed with the direction of F. Well, there is the direction of F. Here is the direction of B, except they're telling us that the direction of B is that way. That's confusing. We would put that direction of B tail to tail with the direction of the magnetic field. Where does that happen? No, with the direction of F. Okay, we don't need to worry about it. Mr. Houghton has just confused himself again. If I were to take this B, which would go from the pivot out to where it acts, and put that arm vector tail to tail, that angle there would be the same as that angle. Cool. But what about this N? That's still confusing. What is that about? Okay. Not resolving that, I pull another equation on. Come on, why don't you pull on? Where I have replaced L by the length of that member which is carrying this current I, and this is this wire right here. So the L that has that current I flowing in it is going to be A long. So I make that replacement, and I got rid of the sign 90. Finally, this torque is being produced here at force 1 and at force 3, and both of those torques are in the same direction and of the same magnitude. So the net torque here is going to be twice this amount, so I lose the 1/2. Then what I'm going to do is note that B times A, here is A and there is B, if you multiply them together, that's the area of this. So BA I replace by area, there's the I, there's the B, the sine theta, then I've added a capital N, and that's to account for the fact that there might be multiple loops here. And each of those loops would be producing the same torque. So if I had 10 loops there, I'd have 10 times as much torque. So that's counting how many loops there are. This quantity, NIA, which sounds like a government agency, is the National Indian Administration. That quantity we are going to call the magnetic dipole moment. That this is a magnetic dipole, and this quantity here, number of loops times the current flowing times the area, is what we call the magnetic dipole. And there you've got mu without the naught. Mu naught is the permeability constant of free space, but mu without is the magnetic dipole moment. So we have to be careful about putting the subscript on when it belongs. If we put this in for that, then we have that the torque that this dipole will experience is equal to the dipole moment crossed with the magnetic field strength. Isn't that lovely? It's exactly the same result that we got when we were talking about electric fields and electric dipoles. Remember, it was a P was the symbol for an electric dipole, but the torque was equal to the dipole moment crossed with the electric field, a capital E here. So this is a cross product of two vectors. Oh, what's the direction of that vector? What do you got here? I got scalar, scalar. A must be the vector quantity. And just like A when we were dealing with Gauss, A is going to be normal to the area. So normal to this area, and that's after all what this arrow here is indicating. That lowercase n, that's the only place I've ever seen that for a normal vector. I have no idea why they did that way. And you will never see it again either. So don't worry about that. But there is a vector that is going normal to the surface. But why that way instead of that way? Well, here is the convention. And here is where I blew it last time. The convention for the direction of the normal to an area. Remember that in Gauss, the direction of the area was always out of the Gaussian surface. Well, here the direction of the area is going to be gotten by a right-hand rule. Now, what you have to see is here is a triangle that we have current flowing around it in this direction. That's a rectangle, isn't it? And then I have taken my hand, and my hand is at the bottom back corner of this rectangle. So this part of my hand is behind the rectangle as we view it. That's why it's faded out there. And I take my right hand and I wrap it in the direction that the current is flowing. Get my fingers to wrap in the direction of the current, and then my thumb indicates the direction of the area. So you will need to remember that to apply this formula. You're going to need to get the direction of the magnetic dipole, of the magnetic dipole moment, and you will need to use this right-hand rule to figure out which way it goes. Always normal to the area, but which way? This concept of magnetic dipole moment, which we've indicated here, again can give rise to torque, which is exactly like the formula that we use for torque from an electrical dipole that we were talking about earlier. And you recall in this case there was also a value for the potential energy, and for the magnetic dipole it's going to be exactly the same formula. It's going to be the dot product instead of the cross product, and there's going to be a negative out front. And so that would mean that you would have your minimum potential energy when the magnetic dipole is parallel to B. Let me get some green here. Oh, that's not green. You're right, Mr. Hoden. So here is a magnetic field, and let's go ahead and we'll go black. If that was the magnetic dipole moment, then this would be minimum potential energy. That's the way the dipole wants to be oriented. If you twisted that dipole, fighting against this, the torque from this magnetic field, if you were to twist it around so it went that way, that would be maximum potential energy. That would be positive. And just like with the electric dipole, when it is perpendicular to the magnetic field, that would mean the area would be lying parallel, but the direction of the area is perpendicular to the magnetic field. That's where we would say you have zero potential energy. Here is a little table from the book looking at the dipole moment of a small magnet, joules per Tesla. The dipole moment of the Earth. Whoa, that's a big number. It's like, oh yeah, that makes sense, because we have I'm sure you have seen people talk about the interior of the Earth being molten, and that there are charges, it's ionized, and some people say it's important that it's nickel in there. I don't quite get that, but that these ions circulating inside the Earth give rise to a magnetic field. But going around in a circle, you know, I failed to say back when we were looking, oh here, at the dipoles, we got nice rectangles, but it doesn't have to be a rectangle. The same result goes if this was circular. You would take the area of that circle. So the shape doesn't matter here. That you would take the area of that times the effective current going around there, and some value for n. You would get a dipole moment for the Earth, and there it is. Electrons and protons have dipole moment, and that is very weird. That is sort of seems to suggest that an electron has spin. Well, they talk about it in quantum physics all the time, the spin of an electron and the spin of a proton. In fact, I believe it's because they have spin that they are fermions. But spin 1/2, an odd half spin makes you a, no it doesn't, it makes you a, yeah, it makes you a fermion. And if you have integer spin, then you're a boson. Yeah, that's pretty important. But if you thought of an electron spinning around, maybe that's sort of like a charged particle running around in a circle, that here you go. Again, we speak about the magnetic dipole moment of an electron. Here is some text from Wikipedia. Oops, we need to get rid of some stuff. which is going to get rid of everything. Go away text. Go away lines. Come back text. Stay away lines. So here, if you want to read it, is this text from the Wikipedia talking about the elementary spin of -1/2, hence a fermion. I should have remembered that. And from this, they come up with a magnetic dipole moment. It's evidently much more complex, and in fact, from my further reading there, it appears that they do not, in fact, go to an NIA kind of approach to get this value for the magnetic dipole moment, but instead they look at the potential energy that the electron has for a given magnetic field. They look at how magnetic fields affect the energy of the electron, and out of this equation is where they come up with the magnetic dipole moment. That then concludes the lecture.